welcome to this explainer. Today, we're going to take a high-speed journey from the microscopic, super intricate workings of your very own eye all the way out to the massive cosmic illusions of the sky above us. It's going to be a fantastic ride through optics, biology, and honestly, the sheer magic of physics.
Here is our roadmap for today. We'll start with the anatomy of the eye, move into vision defects, and then check out prisms and dispersion, atmospheric refraction, and finally, the scattering of light.
All right, let's jump straight into Section 1, Anatomy of the Eye, the Journey of Light.
Okay, let's dive right into the micro world. We're going to trace the exact, phenomenal path that a single ray of light takes from the outside world to become a fully processed image right inside your brain. Light first hits the cornea, which acts as a thin membrane and your initial refracting lens. Next, it passes through the aqueous humor. This is a clear liquid that nourishes the eye with protein, and it also maintains critical eyeball pressure. From there, it enters the pupil. Now, the pupil looks black, but its size is actually dynamically controlled by the iris to manage exactly how much light gets in. Pretty cool, right? Then, the light gets focused by our flexible, crystalline lens, eventually landing on the retina, a highly sensitive screen packed with rod cells for low light and cone cells for bright light. And finally, that signal travels via the optic nerve directly to your brain.
Now, an absolutely crucial part of this whole system is something called the power of accommodation. Basically, this is the incredible ability of the ciliary muscles in your eye to flex and relax. You see, because our eye lens is made of this transparent, flexible, kind of jelly-like material, those ciliary muscles can physically change its shape. By elongating and relaxing, they perfectly adjust our focal length so we can sharply focus on objects, whether they're right in front of our nose or way off in the distance.
Moving on to Section 2, Vision Defects and Corrections, or basically what happens when the mechanics fail.
So, what happens when the physical shape of the eye just isn't quite perfect, causing our incredible autofocusing mechanics to fail? Well, the two most common defects we see are myopia and hypermetropia. Myopia is short-sightedness, meaning you can see near objects clearly, but far-away objects are totally blurry. This is typically caused by an elongated or overly large eyeball. On the flip side, we have hypermetropia, which is long-sightedness. You can see far away just fine, but near objects are a blur. This happens due to a shortened eyeball, or when those amazing ciliary muscles become stiff and the lens just loses its high converging power.
To fix these mechanical errors, we rely on lenses. With myopia, since the eye is elongated, the light converges too quickly and forms the image in front of the retina. To fix this, we use a diverging concave lens to spread the light out a bit before it even enters the eye. With hypermetropia, the eye is too short, so the image actually forms behind the retina. To correct that one, we use a converging, convex lens to help focus the light faster so it lands precisely on the retina where it belongs.
So, how does an eye doctor actually calculate this in the real world? Imagine a myopic patient who can't see anything clearly past 1.5 meters. The doctor needs to bring objects from infinity all the way back to that 1.5 meter point. Using the standard lens formula, they calculate a required focal length of negative 1.5 meters. And since power is 1 divided by focal length in meters, this results in a prescription of negative 0.67 diopters. That negative sign tells us immediately that we're dealing with a diverging, concave lens.
Conversely, let's look at a hypermetropic person who can't see objects closer than 50 centimeters, whereas a normal eye can see clearly at 25 centimeters. The doctor needs a lens that takes an object at negative 25 centimeters and forms an image at negative 50 centimeters. Doing the math, this results in a focal length of positive 50 centimeters, or 0.5 meters. So that requires a converging convex lens with a positive 2 diopter power to bring that reading distance back to normal.
Let's look at Section 3, Prisms and Dispersion, Splitting Light.
Zooming out entirely to the macro world now, let's look at how light itself behaves when it hits different mediums. When white light passes through a simple, triangular glass prism, we get this stunning phenomenon called dispersion. The light bends, or refracts, and literally splits into 7 distinct colors, famously known as VIBGR: violet, indigo, blue, green, yellow, orange, and red. The physics here are absolutely fascinating. Violet light deviates and bends the most, while red light deviates the least. Isaac Newton actually proved this by using a second inverted prism to take those 7 dispersed colors and brilliantly recombine them right back into white light.
Taking this exact concept of light bending as it moves through different mediums, we can apply it to a massive planetary scale. Have you ever wondered why stars in the night sky actually appear slightly raised from their true physical positions?
This grand illusion is entirely due to atmospheric refraction.
Space is a vacuum, a very rare medium, but the Earth's atmosphere is made up of multiple layers that get denser and denser the closer you get to the surface. As starlight travels from the empty vacuum of space into our increasingly dense atmosphere, the light continuously bends towards the normal line. By the time that light hits your eye, your brain traces it back into straight line, completely tricking you into seeing the star higher up than it actually is.
And because our Earth's atmosphere is constantly shifting and changing density, we get a whole host of really cool visual tricks. It's the reason we see an advanced sunrise before the sun actually crosses the horizon, and a delayed sunset after it has dipped below. That constantly swirling atmosphere is exactly what causes the beautiful twinkling effect of the stars too, as the starlight deviates back and forth before reaching your eye.
Which brings us to Section 4, the scattering of light, painting the world.
To understand scattering, which is essentially how light paints our world when it crashes into dust particles, gas molecules, and free water molecules, here's a highly practical, life-saving question. Why are stop signs, traffic signals, and danger signals universally painted red?
It comes down to pure, unadulterated physics. Remember how red deviated the least in our prism? Well, red light has a very long wavelength. Because of this, it scatters the absolute least when it hits particles in the air. This allows red light to pierce straight through dense fog, thick rain, and heavy dust. It travels the furthest distances without getting dispersed, so it can quickly and clearly reach our eyes when danger is ahead. It's a real lifesaver.
On the flip side, shorter wavelengths get scattered heavily by the atmosphere. Violet, indigo, and blue scatter the most. Which brings us to a genuine mind-bending question. If violet is the shortest wavelength and scatters the most out of all the colors, why in the world is the sky blue and not violet?
The blue sky is actually a perfect storm of astronomical physics and human biology. First, shorter waves scatter heavily, and yes, violet scatters the most. But secondly, our sun simply pumps out a much higher concentration of blue light than it does violet light. And thirdly, going right back to the anatomy of the eye we started with, the cone cells in our retinas are evolutionarily far more receptive and sensitive to the color blue than to violet.
Ultimately, everything we've explored today, from bouncing atmospheric light and scattering wavelengths to specialized concave glasses and retinal cone cells, relies entirely on one final silent partner: the brain. The eye is really just the lens. It's your brain that correctly decodes the signals brought in by the optic nerve so we can see the image properly.
Which leaves us with one final, fascinating thought to wrap up this explainer. Our eye lenses are convex, which means they naturally project everything upside down onto our retinas. So if the actual physical image on the back of your eye is completely inverted, is our entire, perfectly stable, right-side-up and colorful world just a brilliant, continuous illusion processed by your brain? It really makes you wonder how much of reality is actually out there and how much is just in your head. Keep questioning, and thank you for joining me on this explainer.